In this video, I'm going to show you what is integral test for series and how we can use these tests to determine the convergence or divergence of series. Consider a series in the general form sigma n from 1 to infinity of a sub n. And consider the integral from 1 to infinity of f of x dx. The relation between this series and this integral is that f of x is the function associated to this series. By associated, I mean the function f of x is a function such that f of n is a n. For example, to have a better understanding of this relation, suppose the given series is sigma n from 1 to infinity of 1 over n. Then the integral associated to this series is integral from 1 to infinity of 1 over x dx. Or if, for example, the series is 1 over n squared plus 4n from 1 to infinity, then the associated integral is 1 over x squared plus 4 dx. So this function is associated to this series. Now, if the integral from 1 to infinity of f of x dx converges, then the series is also convergent. And if the integral diverges, then the series diverges. So actually, the series and the integral have the same behavior. If one of them converges, the other one converges, or if one of them diverges, the other one diverges. But note that you can use this test only if the function f of x, the function associated to the series, is continuous on the interval 1 to infinity, positive, and finally the function should be decreasing on the interval 1 to infinity. So if you want to use the integral test, first you have to make sure that the function associated to the series is continuous, positive, and decreasing. Then you can use this test to determine the convergence or divergence of series. Let's do some examples with the integral test. Consider this series sigma n from 1 to infinity of 1 over n squared. We want to use the integral test to determine the convergence or divergence of this series. If we write a few terms of this series, the first term, if we plug in 1 for n, 1 over 1 squared is 1. The second term is 1 over 2 squared, which is 1 over 4. The third term is 1 over 9. The fourth term is 1 over 16, and so on. As you can see here, the terms of this series are positive and decreasing. So we can use the integral test for this series. The relevant integral to this series is integral from 1 to infinity of 1 over x to the 2 dx. For finding this integral, we can bring x to the 2 to the numerator and write it in the form of x to the negative 2 dx from 1 to infinity. Integral of x to the negative 2 dx based on the power rule for integrals is x to the power of negative 2 plus 1 over negative 2 plus 1. Negative 2 plus 1 is negative 1, and the denominator is also negative 1. So the integral equals to x to the power of -1 over -1. But because this integral is improper integral, we have to write this in the form of limit b approaches infinity from 1 to b. Now if we plug in b for x, this equals to limit of b approaches infinity of b to the -1 over -1 minus, if we plug in 1 for x, 1 to any power is 1 over -1 is -1. Note that b to the -1 is 1 over b. And because b approaches infinity in this limit, 1 over infinity approaches 0. And so the limit of b to the -1 over -1 is 0. 0 minus -1 equals 1. Because the integral is convergent, from the integral test, we can conclude that the given series is also convergent. Let's try another example. Sigma n from 1 to infinity of 1 over n. Probably you know this series and you know this is harmonic series, which is divergent. But here we want to use the integral test to prove that the harmonic series is divergent. If we write the first few terms of this series, the first term is 1 over 1, the second term is 1 over 2, the third term is 1 over 3, and so on. As you can see here, all the terms of this series are positive and they are decreasing. So we can use the integral test for this series. The integral associated to this series is integral from 1 to infinity of 1 over x dx. We know that integral of 1 over x dx is ln of x. And because this is an improper integral, we have to set it up in this form of limit b goes to infinity from 1 to b. Now if we plug in b for x, we have limit of ln of b minus ln of 1, b approaches infinity. Limit of ln of b when b goes to infinity is infinity. Remember the graph of ln of x. If you look at the graph of ln of x, you can see that if we go far to the right, the y values of ln of x gets larger and larger. They increase without bound. And so ln of b when b goes to infinity is infinity. So this limit equals infinity. Note that ln of 1 is 0. And because ln of b when b goes to infinity is infinity, this limit is infinity. And because the integral diverges, we can conclude about the harmonic series that the harmonic series is also divergent. When the integral is convergent, the series is convergent. When the integral is divergent, the series is also divergent. Consider this series, sigma n from 2 to infinity 1 over square root of n. Note that in this series, n starts from 2. But still we can use the integral test for this series. And it doesn't change anything. The only change that we should do in the integral test is that we have to also start our integral from 2. If we write the first few terms of this series, the first term is 1 over square root of 2. The second term is 1 over square root of 3. The fourth term is 1 over square root of 4, which is 1 over 2. The fourth term is 1 over square root of 5, and so on. Again, as you can see, all the terms of this series are positive and they are decreasing. So we can use the integral test for this series. The relevant integral to this series is integral from 2 to infinity. Instead of starting the integral from 1, here we start from 2 because the series also is started from 2. Integral from 2 to infinity, and the function associated to this series is 1 over square root of x dx. For finding this integral, first I rewrite the integrand, the expressions in front of the integral, in the form of x to the power of negative 1 over 2. Note that radical x is x to the 1 over 2. But because we bring the radical x from the denominator to the numerator, we have to make the power negative. Integral of x to the negative 1 over 2 dx is integral of x to the negative 1 over 2 dx is x to the negative 1 over 2 plus 1 over negative 1 over 2 plus 1. Negative 1 over 2 plus 1 is 1 over 2. So this integral equals to x to the 1 over 2 all over 1 over 2 from 2 to b, which b goes to infinity. And we can simplify this and write this in the form of limit of 2x to the 1 over 2 from 2b, and b approaches infinity. Which this equals to limit of, if we plug in the upper bound b, 2 times b to the 1 over 2 minus 2 times 2 to the power of 1 over 2. Because b approaches infinity, b is infinity. To the power of 1 over 2 is infinity. Because b to the 1 over 2 is actually square root of b, and the square root of infinity is infinity. So this limit equals infinity. Because this limit does not exist, so the integral is divergent. And because the integral is divergent, so this series is divergent. With the integral test in general, we can prove that the series in the form of sigma 1 over n to the power of p, n starts from 1, 2 or any other number to infinity, is convergent if the power p is greater than 1. So convergence happens if the power of n is greater than 1. If the power p is equal to 1 or less than 1, then these type of series are divergent. And we name these type of series p series. And it's a good idea to memorize this rule about the p series. P series are convergent for the powers greater than 1 and are divergent for the powers less than or equal 1. For example, series sigma 1 over square root of n from 2 to infinity, the power of n is 1/2, because square root of n is actually n to the power of 1 over 2. And because the power is less than 1, 1 over 2 is less than 1. Based on the p series, based on the rule for p series, the series is divergent. If we look at the other examples that we did in this video, for example, if we look at the harmonic series that here we have, the power of n here is 1. And based on the p series, when the power is 1, the p series is divergent. So as you can see, with this rule, immediately you can figure out the convergence or divergence of these examples. Or if you look at the first example that we did here, the power of n is 2. And based on the p series, when the power is greater than 1, the series is convergent. So I highly recommend you to memorize the rule for p series. P series are convergent for the powers greater than 1 and are divergent for the powers less than equal 1. Let's do another example. Sigma n from 3 to infinity of 1 over n squared plus 9. If you write the first few terms of this series, it is obvious that the terms of this series are all positive and decreasing. The first term of this series is 1 over 3 squared is 9 plus 9 is 18. 1 over 18. The second term is 1 over 4 squared is 16 plus 9 is 25. 1 over 25. The third term, if you plug in 5 for n, 5 squared is 25 plus 9, 1 over 34, and so on. As you can see, all the terms of this series are positive and they are decreasing. So we can use the integral test for this series. The relevant integral to this series is integral from 3 to infinity. Because the series starts from 3, or integral also should start from 3 to infinity of 1 over x squared plus 9 dx. For finding this integral, we can use this formula of the integral. Integral of dx over x squared plus a squared, which in this formula a is a number, is 1 over a tangent inverse of x over a plus c. Note that here a squared is 9, and so a is 3, because 9 is 3 squared, and so a is 3. So this integral equals to 1 over 3 tangent inverse of x over 3. Because this integral is improper, we have to write it in the form of 3 to the b limit b approaches infinity. If we plug in b, this equals to limit of 1 over 3 tangent inverse of b over 3 minus 1 over 3 tangent inverse of 3 over 3. And b goes to infinity. As b approaches infinity, b over 3 approaches infinity. And tangent inverse of infinity is pi over 2. We write 1/3, and tangent inverse of infinity is pi over 2 minus 1/3 tangent inverse of 1, because 3 over 3 is 1, is pi over 4. The angle whose tangent is 1 is pi over 4. pi over 2 times 1/3 is pi over 6. And pi over 4 times 1/3 is pi over 12. If you do a simple calculation here, this equals pi over 12. Because the integral is convergent based on integral test, the series is also convergent. So this given series is a convergent series. But note that we don't know to what value this series converges. Only we know that it is convergent.